Okay, this week we're going to be talking about our last experiment for the lab sequence, which is the Claisen-Schmidt reaction from experiment 19. This reaction, just for your information, is related to the aldol reaction, and so that mechanism that you learned for the aldol reaction is quite similar here. You're going to see a lot of similar things. However, it is different in the sense that we're dealing with an aldehyde and a ketone, not two aldehydes. That's what makes it different from the aldol reaction. It does form a carbon-carbon double bond in the product from this ketone and aldehyde, which we'll talk about here in just a moment. And so that makes this reaction somewhat related to the Wittig reaction. It allows us to form a new carbon-carbon double bond, just like the Wittig reaction allows us to form a carbon-carbon double bond as well. So there are some similarities, and again, this is one of the few reactions that allows us to build molecules up by forming carbon-carbon bonds. So starting with a ketone and an aldehyde, sodium hydroxide, we end up forming this alpha-beta unsaturated ketone. In this case, this is known as a chalcone. It's a special class of molecules that have been used in a number of things, both in medicinal chemistry, industry, etc. And so the carbon-carbon double bond that you see here, the starred carbon comes from the carbon of the aldehyde, and the checked carbon comes from the carbon of the ketone. Very important to note that the aldehyde has no alpha hydrogens, so we don't get any crossed aldol type products. Likewise, the ketone only has alpha hydrogens on one side, the other side doesn't have any alpha hydrogens, and so this allows us the reaction to essentially go to completion. This is a high yielding reaction, and you should get lots of product from this very simple reaction in a fairly quick amount of time. Now, the way that the reaction occurs is starting with the ketone. We know that these alpha hydrogens are acidic, and we're going to use the base sodium hydroxide in this particular reaction to generate the enolate. And the way that that occurs, of course, the base reacts with the acid and pushes those electrons onto the alpha carbon. We could draw the resonance structure for that as well. That's why these are more acidic. The pKa of this is somewhere around 20. And we know that the pKa of water, which sodium hydroxide is a derivative of, is around 16. So the base is actually weaker than the ketone. And so the reaction doesn't go to completion at all here. In fact, you only generate about 1% or less of the enolate at any given moment. Most of it stays as the ketone. Okay, so you generate very little enolate. However, once we generate even a little bit of enolate, it's sitting around with a lot of aldehyde. And so the enolate now attacks the aldehyde in an aldol-like fashion, where that enolate attacks the carbonyl of the aldehyde, breaks that weak pi bond, the electrons go to oxygen. We end up with this intermediate known as the tetrahedral intermediate, also as an alkoxide. This is in the presence of water and alcohol. This is the solvent that you'll be using this week. Alcohol typically has quite a little bit of water in it, so there's plenty of water around. The alkoxide can pick up a hydrogen from water, which generates this beta hydroxyketone, which we learned about in the aldol reaction isn't necessarily stable. And so what happens now is one of these acidic hydrogens gets removed by the remaining hydroxide that we have from the water, eliminates the hydroxide, and we end up with the product plus OH minus. So we start with sodium hydroxide, we end up with hydroxide. It's catalytic in hydroxide. That's why we're only using a single pellet of sodium hydroxide to do this reaction. You don't actually have to weigh it out. A single pellet works pretty well. You might be asking yourself, why is it that the enolate of the ketone only goes after the aldehyde and not the ketone itself? Well, that's a possibility. However, aldehydes are more reactive than ketones, and so as long as we have plenty of aldehyde around, the enolate of the ketone will not react with the ketone itself. It's going to react with the most reactive species there, and that happens to be the aldehyde. Now, the nice thing about this reaction, we're going to be doing this again in a mixture of alcohol and water. As the reaction proceeds and you form the product precipitates out of solution. And so that drives Le Chatelier's principle all the way over here to the chow cone. You'll get this, you'll filter this and dry it, get all of the physical characteristic data that is needed to identify it. And the reaction is one of the simplest that we've done all semester. You basically mix things together, wait a little while, and the product falls out of solution. So it's a really convenient reaction to do, and it's a nice one to finish up the series.